We will move on to Dr. Ben Levine. He's a professor of internal medicine and cardiology at the UT Southwestern Medical Center. He's also the founder and director of the Institute for Exercise and Environmental Medicine at Texas Health Presbyterian Hospital, Dallas, one of the premier laboratories for studying human clinical and integrative physiology. He's served as a co-investigator on several space shuttle missions, on the Russian Mir space station, and is currently PI of a cardiovascular experiment on ISS. He also advises NASA's flight surgeons on cardiovascular medical issues.
Thanks. Great. Thank you, Ellen, and thanks to the organizing committee for inviting me. My job is to do a bit of a deeper dive into some of the research going on in the space program, and I apologize to Kate Rubins. I shamelessly stole this slide from a NASA online presentation, which is really about her work, but it sets the stage for my presentation. Because this is TAMIST, I do want everyone to recognize the tremendous contributions of Gunnar Blomqvist, who was my mentor, the reason I ended up in Texas, and really the father of cardiovascular research in space. Now, what I'm going to do first to set the stage is I'm going to take 40 years of research into cardiovascular physiology in space and distill it into this one slide. The big problem early on in the understanding of cardiovascular system in space was that astronauts fainted. They couldn't stand for more than 10 minutes after coming down, even after short duration space flight. And so much of the early research was devoted to figuring this out. And this slide comes from the Neuralab mission, and this slide shows the stroke volume. That's the amount of blood pumped by the heart per beat in the supine position after 5 and 10 minutes of head-up tilt 2 months before flight. And you can see that with tilting, just standing here in front of you, right, the stroke volume drops by almost 50% and then sort of stabilizes. This is a very reproducible stimulus, so you can see that 2 weeks, 15 days before launch, it's virtually the same. But on landing day, here's the key. First of all, not only is the supine stroke volume substantially lower, but the upright stroke volume is almost 50% lower. So gravity is sucking blood into my feet, and the heart is unloaded. So a lot of work has gone on to try to figure out why that might be. And now I'm going to distill 40 years of ground-based research into one slide. And this comes from some work on our studies, which shows that the reason the stroke volume gets smaller is that because the heart atrophies and gets stiffer. This is a pressure-volume curve with volume of the heart on the x-axis and pressure on the y-axis. And after 5 weeks of bed rest, this curve shifts to the left. So at any given fill pressure, the heart is smaller. So the heart gets less stretchy, it's less full, and it's smaller. And the longer you stay in bed, the smaller the heart gets. So how could we prevent that? Well, our team loves rowing. Rowing is super exercise physiology for the heart. Rowers have the biggest hearts of any athletes, and if you take a group of volunteers, you put them to bed for 5 weeks, and you have them row while they're in bed, you completely prevent this remodeling, completely. So that tells us that doing enough physical activity, loading the heart, prevents this primary adaptation, and none of these individuals after bed rest had orthostatic intolerance. So this is ground-based work, and it sets the stage for one of the largest studies done in the International Space Station era, which is called the Integrated Cardiovascular Study, or ICV. And I partnered with Mike Bungo from UT Houston, and the key to this study was really bringing advanced imaging and human instrumentation to the space station world. These are 3 different kinds of MRIs, both structural and mechanical, and then looking at stiffness of the heart, which we did before and after flight. Now, of course, you can't put an MRI magnet on the space station yet, but so ultrasound, of course, was our primary mode for studying astronauts in flight. And this is a 3D ultrasound image. And as Dr. Sutton mentioned, we don't have sonographers in flight, right? We have astronauts. So how the heck are we going to get them to do high-quality ultrasound in space? And so Doug Hamilton and Ashat Sargassian, working with Scott Dilchovsky, came up with this spectacular strategy of remote guidance. So basically, they have this instruction manual, and they call on the telephone to David Martin down at Johnson Space Center, and he says, okay, put the probe here, twist it 10 degrees this way, slide it down, and we get perfect images. It's really quite spectacular. And this has now been used extensively in ground-based opportunities. We also did a lot of very detailed, in-depth human instrumentation, which, for example, this particular tool allows us to get beat-by-beat blood pressure. This is 2 weeks before return from space. Each one of these spikes is an arterial blood pressure measurement. You can see it at rest, during exercise, and even these surges that occur during sleep. We also did some extensive monitoring of the electrocardiogram using long-duration Holter recordings and looking at high-resolution signal averaging of the P waves, the QRS, T-wave alternans, and a lot of fancy stuff that you don't really need to know. So what did we find? Well, we went to the International Space Station. We looked at 13 subjects, 9 men, 4 women, pretty typical astronauts. Remember, mean age of the astronauts who are flying is in the late 40s. These are not 20-year-olds, okay? And so here's a good example of some of the first data. This is tissue Doppler imaging. Just think about this as diastolic function, how the heart relaxes and fills. And what I'm showing you is the filling of the heart at 0 degrees, so flat like this, no head to foot gradient, equivalent to being in space, 22 degrees, which is equivalent to Mars gravity, 41 degrees, which is equivalent to the load that an astronaut would experience during a landing on Mars on another planetary surface, and then upright on Earth. And you can see that the filling of the heart is exquisitely sensitive to gravitational gradients. And what happened when these astronauts came back? Well, that's quite interesting. And this is the first time anyone's ever tried to look at what's going to happen at Mars gravity to the heart. Right? Obviously, we like it not to be the first time we ever look at it, to be when we land on Mars. And so it's nice to see that cardiac filling is pretty normal on Mars gravity. Actually, perhaps not as much as in the supine position, but better than standing upright before flight. So that's pretty good news. During flight, these are the data. What you can see is quite interesting. When we first made the measurements at about 30 days, it looked like the filling had deteriorated. And that's because the astronauts don't have as much time to do stuff, their countermeasures when they first get there. It's quite busy. But over time, over the 6-month period, they actually started to restore cardiac function towards normal. Now, this is cardiac filling. What about the size of the heart? And this is the echocardiographic volumes. LVEDV is left ventricular end diastolic volume in the supine position, so space-like gradients, all the way down to upright Earth gradients. What do you think happened after 6 months in space? Well, here's the data. In the supine position, the heart's volume was somewhere between supine and upright. And at 22 degrees Mars gravity, the heart size was bigger than it was when standing upright before flight. Again, evidence that 6 months of flight, given adequate countermeasures, does not deteriorate cardiac function or structure beyond just what it like in the upright position. And we saw the same pattern with a lower volume early, and then after 6 months towards the end of the flight, the heart actually gets bigger. It doesn't continue to get smaller. So we turned to cardiac MRI and said, okay, are we going to see the same atrophy that we saw in bed rest? And we didn't see anything. I mean, it was absolutely flat before and after 6 months of flight. 108 grams, 109 grams when they came back. That's really interesting. But I will say there was a fair amount of individual variation. And why? So can we learn something from that individual variability? And here's our fittest astronaut, a male, who had a volume and a mass shown here. And after 6 months in space, the volume was down, the mass was down by about 11%. That's about half as much as we would expect. But our least fit astronaut, you could see this person is smaller. So the mass is smaller and the volume is smaller before flight. But after flight, her heart's actually bigger. She developed physiologic athletic hypertrophy of the heart while she was in space. And she told us she never did as much exercise in her entire life as she did during her mission in space. So if you try to plot the actual work of the heart versus the change in the left ventricular mass, it's a pretty good relationship. So the bottom line is, the more work you do of the heart in space, the more you can prevent the loss of the cardiac mass and cardiac atrophy during long-duration spaceflight. Well, the other thing that has driven a lot of the research in space is cardiac arrhythmias. And this comes from our Holter monitoring, and I want to point out to you that we see lots of arrhythmias. I mean, this is what happens when you monitor middle-aged men and women. You see lots of arrhythmias, pre-flight, in-flight. I mean, looks like second-degree heart block for those of you who know how to read an electrocardiogram. But all these little extra squiggles are not normal, but they're common, and they were present as much pre-flight as in-flight. And so here's, again, a lot of data in one slide. These is every single astronaut, and the numbers of extra beats in 48 hours of monitoring on a log scale. So some people had very few or none. One person had almost 10,000